Hi, I am Abdullah Al-Fararja. Today I will present our research paper titled A Class of R-Star Tree Indexes for Spatial Visual Search of Geotagged Street Images. As you know, nowadays many smart city applications are image-based. These applications include traffic management, monitoring air quality, and street cleanliness. Such smart city applications are built using machine learning algorithms, which require training on a set of similar images within a specific geographical region. While taking a photo or recording a video, the new trend is to capture relevant metadata, including location. As a result, we have large-scale geotagged image datasets. These images are collected by both normal users and companies. The massive sizes of user-generated images resulted due to the ubiquity of smartphone users and the improvements in network bandwidth and the growth of image sharing online services. For example, Flickr collected more than 200 million geotagged images. On the other hand, an example of professional generated images are the ones collected by Google Street View. In particular, Google collected photos for more than 3,000 cities all over the world. As a result, urban streets are documented by geotagged images. With the availability of massive sizes of geotagged images, a visual data management is data. Especially such visual data management is getting more important in various applications, from simple image search to sophisticated machine learning. The visual data management can be used in searching geotagged images in multiple forms. One way is to search for similar images using an example image. Another way is to retrieve the images within a geographical region. Hence, it seems natural to combine these two mechanisms to search images based on both spatial and visual relevance. We refer to such type of search as spatial visual search. Particularly, it is the mechanism of finding similar images to a given query image and simultaneously within a given geographical region. This type of a new image search requires developing a new index structure for efficient search. Before discussing index structure, I will just give a brief introduction how we can represent geotagged images in terms of both spatial and visual features. For spatial representation, an image can be represented straightforwardly using its camera location. However, the shortcoming of the camera location is that the scene depicted in an image can be in any direction and distance from the camera. There is another representation that requires more metadata collected from several sensors, and this representation is known as image field of view, which is the spatial extent of an image. This descriptor provides a precise representation. However, it might loosely representing the spatial extent, especially when the camera is far from the scene depicted in an image. Alternatively, we have another spatial representation, which is scene location, that is a partial region of the FOV descriptor. In terms of visual representation, we can represent an image visually using multiple features such as color, texture, and shape, and also convolutional neural network image features. Recently, CNN showed successful results in multiple computer vision tasks such as image classification and object detection. These studies, other studies also showed that CNN can be used to extract rich feature vectors for image retrieval. In our work, we use CNN features as visual representation and scene location as spatial representation. In this research work, we focus on street images. When focusing on street images, we have a key observation that similar images are usually located in the same neighborhood. We call this phenomena as locality of similar visual features of street images. To validate this phenomena, we did an analysis which is illustrated in this simple visualization. Basically, we calculated the difference between the similar images for a query image from the ones located in the spatial proximity. If we look at the figure in the left, where most of the similar images are located in the same neighborhood of the query image, this shows high locality. Otherwise, it will show low locality. We have experimented this phenomena using dataset of street images collected at 4 different locations, as shown in this figure. Across all of the examined datasets, at least 80% of the top 10 similar images are located in the neighborhood of a reference image. Consequently, these results confirm the validity of the locality of similar visual features observation. Based on this observation, we thought that, okay, using a spatial index is potentially sufficient for organizing geotagged street images. Thus, we can just forget about visual indexes and focus on spatial indexes. Based on the previous observation, we started building a class of R-star tree for spatial visual search. As baseline, we use the conventional R-star tree for organizing images using only their spatial properties. Meanwhile, the leaf nodes are augmented with both spatial and visual properties. On the contrary, R-star tree is used for organizing images using only their visual properties. However, to ensure good performance of the index, each image is represented using its dimension reduced visual descriptor. Both of these baselines have problem with the performance because they are organized using only one type of properties. Thus, pruning search space can be done using only one of the properties, which potentially lead to many false hits. To do better performance, we use R-star tree for organizing images using their spatial and visual properties. Basically, each node has an MBR of the spatial and dimension reduced visual properties of the contained images. This approach can outperform baselines. However, this approach treats spatial and visual properties equally, even they belong to different spaces. Also, when treating these properties equally, this approach cannot benefit from the phenomena of street images where similar visual features are located in the same spatial locality. So the question here, can we treat these two types of properties differently to give more weight for the spatial properties while organization? So the proposed second proposed index is to associate each node with 2 MBRs, one for spatial and one for visual properties. Also, we can adapt the visual organization by setting different weights for the spatial and visual properties. For adaptation, we extend the calculation of the 3 optimization criteria used in R3. For each criteria, the optimization value for spatial and visual properties are calculated separately and then linearly combined. In this way, we have a general design. When setting a full weight for spatial properties, the index becomes analogous to spatial R star tree. Meanwhile, when setting a full weight for visual properties, this index becomes analogous to visual R star tree index. In the case of street images, we found that it is better to set the weight for spatial properties more than 0.5 to get benefit from its unique characteristic. To validate our indexes, we conducted several experiments using real dataset obtained from Google Street View for 5 geographical regions: Orlando downtown, Pittsburgh downtown, Manhattan, and the neighborhood of USC and San Francisco. The figures below shows the heat map of each dataset. These datasets are different in terms of their spatial region and spatial density. Also, the largest dataset which we have is San Francisco dataset, which contains more than 500,000 images. The evaluation, we reported the evaluation using two metrics, efficiency and effectiveness. The left figure shows the efficiency of our approaches. It's as shown in this figure, all hybrid indexes outperform the baseline because of using both image descriptors in pruning the search space, in addition to the hybrid organization in these indexes. As a specific example, using Manhattan dataset, which is spatially sparse, the performance of the hybrid indexes obtained a speedup factor reaching up to 1.6. But when using a spatially dense dataset, the hybrid indexes can do better job, and these hybrid indexes obtained a speedup factor up to 4.8. In a high spatially dense data set, we have more images in a local region, potentially, which this potentially increase the similarity among images in that region, hence increasing the locality of similar visual features. Therefore, our hybrid indexes can do better job. In terms of effectiveness, as shown in the right figure, spatial R star 3 index always achieved a perfect recall score because it does not use dimension reduced descriptor for the image organization, while the other indexes do, hence obtaining a lower recall score. Regarding the hybrid indexes, they achieve better recall compared to the other baseline. ASV achieved better recall score reaching up to 0.94 compared to BSV because of prioritizing backing the images located in the same neighborhood together in the same node. Here we show the evaluation of our indexes in a large scale data set, which is in San Francisco data set. With such data set, with such large and dense data set, our hybrid indexes showed much better performance. In particular, ASV achieved a speed up factor of 18x and a recall score of up to 0.94. Here is the list of related work. I will skip them because of time limitation. In summary, I can say that this paper proposed a novel spatial visual indexes for geo-tagged street images. We extended a spatial-based index to be better option for spatial visual search. Our experimental result demonstrated the efficiency of our proposed hybrid approaches. We believe that spatial visual search can be used for many applications, including smart city applications. That's it. If you have a question, please contact us via email. Thank you.